Welcome. This is a tutorial on fuzzing surge mail 3.8 K4-4. I've already pre-configured the base code for this, so we're going to go ahead and save this into this folder in here so that when we do MSF updates, we won't have to worry about overwrites. Now that saving is complete, we're going to go ahead and launch MSF console. While that starts, we're going to go ahead and go over to our target machine and launch Immunity Debugger. We're going to go ahead and attach it to the surge mail process, which is already running on this machine. Go ahead and show you that we don't have anything already pre-configured, like any breakpoints from this particular exploit. So let's go ahead and take a look at the actual module now. I'm going to go ahead and load up the auxiliary module, and I'll show you that we have already pre-configured our options by loading an RC file at startup of MS Console. This saves a lot of work later on. As is, this fuzzing module will create random data all the way up to 1024 bytes. We're going to go ahead and skip forward a couple minutes so that we can see that we actually were able to produce a crash. We're going to go ahead and take a look at that crash now. As we see, this byte actually hit at 1007 bytes. So if we go ahead and examine our debugger and take a look at the SEH stack, we can see that we were unable to get an SEH overwrite even though a crash did occur. Our first attempt to overwrite SEH failed, but by sending an overly large buffer, in this case 1000 bytes of the character A, we can see if we can generate the type of crash that we're looking for. We save our changes and go ahead and reload the module and then run the module to see what occurs. This time we immediately hit a crash. So going back over to our debugger, let's take a look at the handler for the SEH chain a little bit better. Look at that. SEH has been overwritten by our character A, 41. So if we follow this address into the stack, we can actually see that we are able to overwrite everything that's there. This means there's a good chance that we can actually go ahead and overwrite SEH with high success. After a quick restart of the debugger, we now need to figure out where exactly in our 11,000 bytes we were able to actually overwrite SEH. To do this, we're going to go ahead and use the text.pattern function already available to us inside the framework. Once we've saved this modification, we go ahead and reload and rerun the module to see what actually occurs. As expected, our code does go ahead and generate the crash. An inspection of the SEH chain shows that we were successfully able to overwrite our SEH handler with the value from our buffer. Now we have characters of interest that we need to examine a little bit more closely to figure out where they fall. Now that we know the exact bytes that overrode our SEH handler, we need to figure out where within the text pattern that we sent this particular pattern exists. Here is the exact value that was overwritten and the amount or the size of the buffer that we actually sent, in our case 11,000 bytes. The result of our previous calculation provided us with an offset of 10,360. We're going to go ahead and modify our fuzzing code just a little bit now so that we can send 10,360 bytes of the letter A, followed by 4 bytes to overwrite SEH, followed by 636 bytes to fill the remaining 11,000 byte buffer. This modification of our code will allow us to go ahead and prove that we're able to successfully overwrite the SEH handler with exacting precision, which will enable us later to fully develop an exploit that will work for this. Running the exploit now will prove that we were able to overwrite our SEH handler with the values that we intended to in the correct location. We intended to overwrite our SEH handler with 42424242, which here we see that we were successfully able to do. Now on to exploit